tutorial, by the mercies of God, we'll be able to solve the physics past paper that was written by GCE candidates in 2025. The first question says, accurate measurements of physical quantities is essential to more scientific investigations. Measurements help scientists determine the relationship between quantities. And the first part says, explain what is meant by physical quantity. Well, a physical quantity is basically the measurable property of a body. As for example, length is a physical quantity. So here I wrote the answer as a measurable property of a body. Alright, question B. Express 1 megabyte in scientific notation. Okay, so we should remember here that mega is a prefix for writing 1 times 10 to the power 6. So 1 megabyte in scientific notation would be 1 times 10 to the power 6 bytes. Okay. Then question C. State one basic physical quantity and its SI units. So here my answer was time, and the SI units for time is seconds. There are numerous answers that we can give here. We can also say mass, we can also say temperature, and we can also say light intensity. Furthermore, we can also say length. Alright. Then question 2. A body of mass 4 kg at rest is a body of mass 4 kg at rest is acted on by a resultant force which varies with time as shown in figure 2.1. The first question says define force. Force is defined as a push or a pull exerted on a body by another body. So what I'm trying to explain here is that force will be a product of the interaction between two or more bodies. Alright. Then question B. Determine the rate of change of velocity in the first 6 seconds. If we correctly analyze these words here, rate of change of velocity, they're trying to describe something, and what they are describing is the word acceleration. Because remember, acceleration is the rate of change of velocity. So meaning that this question is requiring us to find the acceleration in the first 6 seconds of the motion. So how do we do this? Let's go back to this diagram. The first thing that we should do is to get the data. The data here that we have is that the mass is 4 kg and the force when time is 6 seconds, force is equal to 15 newtons. Acceleration, we do not know. Okay, so remember this formula that links force, mass, and acceleration from Newton's second law of motion that says that force is equal to mass times acceleration. We're saying that force, if we substitute, it is 15 newton. Then the mass, it is 4 kg. Acceleration, we do not know. Dividing over 4 on both sides of the equation, we have that acceleration is 3.75 meters per second squared. So this was the rate of change of velocity in the first 6 seconds of the motion. Question B2. Find velocity after 6 seconds. We can use the formula here that says that acceleration is equal to v minus u over t. Alright, are we given all the information? Let's check from the graph. So we're saying that the formula to find the final velocity is this over t, where a is the acceleration. We already know this, we have calculated it. V, it is the final velocity, which we are yet to calculate. Then u means the initial velocity. From the information given by the question, we are told that a body of mass 4 kg at rest. At rest here means that the initial velocity of the body was 0. Okay, then the time we are told in the first 6 seconds. So if we substitute with the given information, we will have that the acceleration is 3.75 v minus 0 over time, it is 6 seconds. If we multiply 6 times 3.75, I'm getting v to be 22.5 meters per second. Okay. Then question 3. Unfortunately, this question is on graphs and other stuff. The technical capabilities of my device cannot display the solutions for this question, so please pardon me on this one. Okay, so let's quickly go to the next one. Question 4. Figure 4.1 shows a spanner called a moorwrench used to unscrew a nut from a bolt. The average force applied to the moorwrench is 20 Newton. Question A1. Define a moment of force. By definition, a moment of force is the turning effect of a force about the pivot. So this is what we call the pivot. So here we're saying that moment of a force is the turning effect of a force about the pivot. So in other books, instead of using the word pivot, you sometimes find this word fulcrum. About the fulcrum should be you here. Okay, so it literally means the same thing. Then question A2. Calculate the moment if the 20 Newton force is applied 30 centimeter from the center of the bolt. Okay, so what we have that the formula of moment is given by force times distance. The force is 20 newtons and the distance that we are given from the question is 30 centimeters. However, in physics, we are advised to use units that are in meters rather than in centimeters or kilometers or any other units. So to convert the 30 centimeter to meters, we basically divide it over 100. So this would give me 0.3 meters. So I'll substitute here 0.3. So if I total, I'm getting a value of 6 Newton meter as my moment. Then question B. The nut could not unscrew when the 20 Newton force was applied at the position shown in figure 4.1. Suggest 2 changes that should be made to increase the moment. So I earlier cited that the formula of moment is force times distance. This formula here outlines that the moment of a force is determined by only 2 factors. Number 1, the size of the force. So in order to increase the moment of the force, we should increase both the size of the force and the distance applied from the pivot. Okay, so here my answer was that increase the size of the applied force. This would increase the moment. And number 2, increase the distance of the applied force from the pivot. This as well increases the moment. Question C. what type of simple machine is a moment? A moment is a type of simple machine called a lever. Because if you remember the definition of a lever. The definition of a lever is that a lever is a rigid bar that turns about a fulcrum, and this is very closely related to how a Moore wrench works. A Moore wrench also has two bars here that would turn about this fulcrum. So that's why we're saying that a Moore wrench is a type of simple machine called a lever, because they both work under the same principle of a turning effect of a force. Question 5. Pressure in cutters must be kept at recommended pressure levels. That pressure is monitored regularly so that required action is taken if the pressure is not at the correct level. Question A1. Define pressure. Pressure is defined as force acting normally per unit area. And this word normally is very important because it describes that this force, that the applied force will act at right angle to the area in contact. That's why we're saying that pressure is force acting normally, meaning at right angle to the applied area, so to the area. Okay. Then question A2. Derive the SI unit for pressure. Remember, the SI unit for pressure is basically Newton per meter squared. So these are the units that the examiner wants us to derive. Remember this formula that says pressure is equal to density times gravity times h. Alright. The SI units for density, since density is mass over volume, right? And we know that mass is measured in kg in physics and volume is in meter cube. So we will place here kg over meter cube multiplied by g. The SI units for g, which is gravity, they are 2. G, it is equal to Newton per kg. G is also equal to meter per second squared. So in this case, we'll take this SI unit for gravity. So we place here Newton per kg multiplied by h. H is the height, and height is measured in meters. So we have meters here over 1. Okay. So if we divide this in this, meaning that the kg will go, and meter here will cancel 1 meter from this meter cube, so that we remain with our final answer of Newton per meter squared, which is exactly the SI unit for pressure. Then question B, figure 5.1 shows an instrument for measuring pressure. The atmospheric pressure acts at point Z, and the gas pressure to be measured acts at X. Explain how the pressure at X compares with the pressure at Z. Alright. So here, guys, we should be aware that there should be 3 ways in which EZZ can phrase this question. Okay, let's suppose the pressure at Z is greater than the pressure at X. How would the diagram look like? Alright, so we have the diagram looking something like this. Okay, so if the pressure at Z is greater than the pressure at X, it means that the manometric liquid towards the limb for Z would be at a further distance as compared to the manometric liquid at the limb for Z. So it would be something like this. Okay, so on this side, on the side for X, the manometric liquid would rise to a higher level as compared to the side of Z. So that's how the diagram would look like if the pressure at Z is greater than the pressure at X. Okay, then suppose that the pressure at X is greater than the pressure at Z. How the diagram look like? Okay, so we have our diagram like this. We're saying that we have made a fact to say that the side where the pressure is greatest will have like less of the manometric liquid. So if X has a higher pressure, it means that the manometric liquid on the side of Z will rise to a higher level. So they will rise to a higher level as compared to the side for X. So this is exactly how the diagram is looking like. So this means that the pressure at X is greater than the pressure at Z. That's the only way in which this diagram would come to be. Therefore here, my answer was that the pressure at X is greater than pressure at Z. Then question 2, the pressure at Y. Okay, so if we notice, both X and Y are at a steady level. They are on the same level. So if this happens, it means that the pressure at X is exactly equal to the pressure at Y. So here I wrote pressure at Y is equal to pressure at X. Question C. The manometer liquid used in figure 5.1 is water. Its density is 1000 kg per meter cube. If the length from Z to Y is 25 centimeter, determine the difference in pressure at X and at Z, taking G to be 10 Newton per kg. So we are told that the distance from Z to X is 25 centimeters. The manometer liquid used in figure 5.1 is water. Its density is 1000 kg per meter cube. If the length from Z to Y is 25 centimeter, determine the difference in pressure at X and at Z. Okay. So we thought that the length from Z to Y is 25 centimeters. Alright. Remember, pressure in fluids is given by the formula density times gravity times height. The density of water, which is the manometric liquid used, is 1000. The gravity we've been given to use as 10, and the height is 25 centimeters. However, the SI units for the height that is used is the centimeter, but this is wrong because in physics we are advised to use units that are in meters. So we divide this over 100 to get 0.25 meters. So here I will place 0.25 meters. Doing my calculation, I should get a value of 2500 pascals as the pressure. Question 6. Figure 6.1 shows a ray of light incident from air into an optical fiber made of glass whose refractive index is 1.5. The light ray is incident at B at an angle I and leaves B at angle R. It then strikes the wall of the fiberglass at P at an angle of 53 degrees. Question A. Calculate Roman numeral 1 angle R. To calculate the value of angle R, we'll use the property of a triangle that says that the sum of interior angles in a triangle is supplementary, meaning that if we add all the interior angles in this triangle, we should equal to 180 degrees. So what do we have? We have that there's a right angle there. So we're saying that R plus 90 degrees plus 53 degrees should give me 180 degrees. R is equal to 180 degrees minus 143 degrees, meaning that the value of R is 37 degrees. Okay, then question 2, calculate angle I. How do we find angle I? We find angle I by using what we call Snell's law. Remember, Snell's law tells us that the ratio of the sine angle of incidence to the sine angle of refraction is a constant. And that constant in Snell's law is what we call the refractive index. So what do we have? From Snell's law, we have that the refractive index, represented by this letter here, is equal to the sine angle of incidence over the sine angle of refraction. So far, we have the angle of refraction as well as the refractive index. So we can easily work out the angle of incidence. Doing the substitution, I'll have that n will be 1.5 is equal to sine I over sine 37 degrees. Okay, so sine inverse of the product of 1.5 times sine 37 degrees. Let me take this here, where I is equal to this. So what do we have? We have that I is equal to, let me quickly calculate. Okay, so we have that I is equal to 64.45 in dollars numbers. So this is approximately equal to 64.5 degrees as our angle of incidence. Then question A3, the critical angle of the glass fiber. Remember this formula that relates critical angle that says that like this. So the sine angle of the critical angle is equal to 1 over the refractive index. The refractive index that we have for glass, it is 1.5. So what we have here is that C is equal to sine inverse 1 over 1.5. So this would give me a value of 41. So this is approximately equal to 41.8 degrees. So this is the critical angle of the glass fiber. Question B. Explain how the ray manages to travel through the glass fiber and leaves at the other end of the fiber. So how is the ray, like we're told to explain how the ray manages to leave at the other end of this glass fiber. So the reason as to why this is so is because this ray undergoes repeated total internal reflection. Okay, so it undergoes repeated total internal reflection. That is the reason why it is able to live at the other end of the glass fiber. And we should remember that total internal reflection is dependent on two factors. Number one, the angle of incidence I should be greater than the critical angle. That's the condition in which total internal reflection will occur. And the second condition that total internal reflection will occur is that the light ray should be traveling from a dense medium to a less dense medium, and a less dense medium is in most books referred to as a rarer medium. Okay, so that's the reason why it is able to live at the other end of the glass fiber. So here I presented my answer to say that the ray repeatedly undergoes total internal reflection in the dense medium that enables the ray to live at the other end. Then question C says, state one use of optical fibers. Well, optical fibers are used in telecommunication. So here I said used in long distance communication. It's basically the same. Okay. Oh, there's no question 7. Let me check. In 7a, state Faraday's law of electromagnetic induction. Well, Faraday's law of electromagnetic induction tells us that the magnitude of induced electromotive force in a conductor is directly proportional to the rate at which the conductor cuts across the magnetic field lines of force. So that's what I wrote in my answer. So in my answer, I said the magnitude of induced electromotive force in a conductor is proportional to the rate at which the conductor cuts across the magnetic field lines, meaning that if a conductor cuts across the magnetic field lines more rapidly, then we'll have a greater amount of induced EMF. And here it is very, very important that we avoid writing the word induced current, because induced current can only take place when we have a closed loop. The first thing that takes place in electromagnetic induction is that when a conductor cuts across the magnetic field lines, what we produce through the conductor is an EMF. It's not an induced current first. An induced current would only take place when we form a closed loop. Now, suppose we don't have a closed loop, but we just have a conductor. Then in such a case, it's only an induced EMF that is present, not an induced current. So here, it is very important that you say induced EMF by writing the word electromotive force. Okay. Then question B says, B, figure 7.1 shows a diagram demonstrating electromagnetic induction. Question 1, use arrows to show the direction of induced current in the coil on figure 7.1. In order for us to predict the direction of the induced current, then we should use Fleming's right-hand rule. Remember, for electromagnetic induction, in order to predict the direction of motion or current or magnetic field, we use Fleming's right-hand rule. Then, for magnetic effect, we use Fleming's left-hand rule. But in this case, it is electromagnetic induction. Therefore, I emphasize again, we are using Fleming's right-hand rule. Well, Fleming's right-hand rule tells us that if we position the thumb, the first finger, and second finger of the right hand mutually at right angle to each other, okay, so like that, so they should be at right angle, to each other. And we should remember that the thumb should point in the direction of motion of the conductor. Then the first finger should point in the direction of the magnetic field. Then the second finger should point in the direction of induced current. Okay, so in this case we're given two. We're given the motion as well as the direction of the magnetic field, which is in this direction, because magnetic field lines will run from north to south, so they are in that direction there. Okay, so meaning that I'll have to position my thumb upwards. Should do this. So position your thumb upwards. Then the the first finger should go in this direction. Okay, so in that direction. If you have successfully done that, you'll find that the second finger is pointing in this direction, meaning that the direction of our induced current is in this direction here. So it is like this. All right. Okay. The second alternative that we could have used in predicting the direction of the induced current is by basically observing the direction in which the needle of this galvanometer is deflecting. So as you can see, the needle of the galvanometer is deflecting in that direction, meaning that that is the direction of the induced current. Okay, so instead of using Fleming's right hand rule, you can also use this observation. But Fleming's right hand rule is very important because there are some instances in which you are not given this galvanometer here, so you should know it by heart. Then question B2 says state one method by which the induced current can be increased. So one method in which B2 state one method by which the induced current can be increased. So one method by which we can increase the induced current is by increasing the speed at which the coil is moved. Here I didn't finish. We should also include the weight across the magnetic field. So if the speed at which the coil is moved across the magnetic field is increased, remember from Faraday's law of electromagnetic induction, we have that if the rate at which the conductor cuts across the magnetic field lines is increased, then the size of the EMF would also increase. So that is what we do here. Another way we can increase the size of the induced current is by using stronger magnets, because stronger magnets will produce a strong magnetic field. Okay, then another alternative that we could have written is by saying that we increase the coiling of the coil, because when we increase the coiling of the coil, we're basically increasing the length of the conductor, meaning that we'll have a greater length of the conductor cutting across the magnetic field lines. So this as well increases the size of the induced current. Then question C, figure 7.2 is a graph showing variation of EMF with time. EMF stands for electromotive force. Why is there no induced electromotive force at C and at E? Okay, so if this graph were for a generator, then so in this case it would be an AC generator. because an AC generator will have the direction of induced EMF changing periodically, so it would be going up and down. It cannot be a DC generator. So if this is an AC generator, then point C and E would be the points where the coil, you should remember this, okay, where the coil is vertical. And when the coil is vertical, it means that the direction of the magnetic field lines is in the same direction as the direction in which the coil is moved. So in such a case, there are no magnetic field lines that are cut. And if we have that, there is no magnetic field lines that are cutting, then we cannot have an induced current. Therefore, at C and E, I wrote because at the point C and E, the coil is vertical, hence no magnetic field lines are cut to cause an induced electromotive force. Okay. Then question B says, explain why B represents maximum forward current. Okay, so this is forward and this is backward. The reason why this is maximum forward current is because in this direction, that is where we have the maximum EMF moving in the positive direction. In this case, we have the maximum at D, we have the maximum EMF moving in the negative direction. So here I presented my answer to say that because that is where there is maximum positive induced EMF, and the key idea and the key word here is positive. This is in the positive direction. Okay, all right, let's go to this next question. The next question D is saying, state one application of electromagnetic induction. So knowledge of electromagnetic induction is widely applied, and number one application that we can make mention of is in construction of transformers, and the second application is in bicycle. Question 8. Figure 8.1 shows an electronic circuit involving logic gates in its operation. A. Explain what is meant by logic gate. Well, by definition, a logic gate is a switching circuit in an electronic system that uses binary inputs to produce binary outputs. So this means that a logic gate will actually get to work with only two numbers, and those two numbers are 0 and 1. In a logic gate, 0 means low, which we can think of as being off. Okay. Then 1 means high, which we can think of as being on. Right. Then the B part of the question says, name a single gate that is equivalent to the combination of the gates in figure 8.1. So we have that in figure 8.1, we have this gate and this gate. This gate here that is shown here is what we call an AND gate. And this gate that is shown there, it's what we call a NOT gate. So when we combine an AND gate plus a NOT gate, the resulting gate is called a NAND gate. So that was my answer for this question. I wrote NAND gate. Question C. Complete the following truth table for the gates in figure 8.1. So to better explain this, let me withdraw this truth table on this part. Okay, so this is the truth table that we are completing. Let us answer this question step by step. So we earlier established that this gate here, it is an AND gate, and this gate there, is a NOT gate. So for us to successfully fill in all these values, we'll have to draw the truth tables of both this AND gate as well as a NOT gate. So let me start with an AND gate. Okay, so the possible combinations that we have on this AND gate would be 0 0 1 1 and 1 0 1 0. Okay, so for an AND gate, you could basically think of it as two switches that are connected in series to each other, and in this connection we have a light bulb connected to a power supply to provide electrical energy. Alright, so then if the bulb lights up, it means that the output is 1, because we earlier cited that 1 means high, which we can think of it as being on. So if the bulb is on, then meaning that the output is 1. But for a series connection, the light bulb can only be on if both of these switches are closed. If both switches are closed, that is when the output can be 1. And the closing of the switches would mean that the input is 1. So where we have both inputs being 1, that is where the resulting output would be 1. So 1, 1, meaning that the output would also be 1. Okay, so both switches need to close so that the output is on. That is why we are saying the input should be 1 and 1, so the output is 1. Okay, then if you think about it, in the in a situation where only one input is 1 and the other input is 0, meaning that in a case where only one switch is closed and the other switch is not closed, then the light bulb cannot light up, meaning that the light bulb would be off, or simply it would be, meaning that the output would be 0. So in all situations where the output is not 1 1, then the resulting, where the input is not 1 1, then the resulting output would surely be 0. So in all cases the output would be 0. Okay, how do you draw the truth table for a NOT gate? For a NOT gate, its truth table is very easy to draw. It only has one input and one output. Okay, so we have 0 and 1. So a NOT gate is sometimes referred to as an inverter, because what a NOT gate does is that it flips the input value. So if we're imputing 1 into the logic gate, then the output would be 0. And if we're imputing 0 into the NOT gate, then the resulting output would be 1. So the logic gate will act as an inverter. With this said, let us finish this truth table that the examiner tasked us with. Okay, the first part, let me use this color. This one. Right. The first part, if the input at S is 0 and the input at T is 0 as well, then we have that the resulting output at Y would be 0. If you check, 0 0 gives 0 output for an AND gate. Then at Z, since this gate in between here, it is a NOT gate, and the NOT gate we have established to say that it acts as an inverter. So if we have a Y, if we have that Y is 0, then the NOT gate would flip this value to being 1. Okay, if you check here. And if we have that the input at S is 1 and the output, and the other input at T, is 1, then the resulting output at Y would be 0 if you check on this part. Okay, but here we are saying that the NOT gate would flip this value to being 1. The other combinations for this circuit we have is 0, 1, and 1, 1 there. Okay, also on this part, if the input at S is 0 and also the input at T is 1, then the resulting output at Y would be 0 if you check this part of the truth table of an AND gate. But the NOT gate will act as an inverter, so it would flip this to being 1. Alright, in the last scenario, if both inputs at S and T are 1s, then the resulting output at Y would be 1. You should check on this part. So we would have at Y 1. But the NOT gate would flip this value. If you observe, it is flipping this value to 0. Okay, so we have successfully completed the drawing of a NAND gate truth table. Let us go to the next question. It says the heat sensor consists of a thermistor, resistor, and power supply. In the space given, draw a labeled circuit diagram of a heat sensor showing the components connected. Alright, so before we start drawing the circuit diagram, let us let us get to draw the circuit symbols of each electrical component. Started with a thermistor. The the symbol of a thermistor is like this. Then for a resistor, it is drawn something like this. Then for a power supply, this is where you need to be careful, because for a power supply, the electrical symbol, it is like this. I was told when the question has specifically said power supply, it has not said battery, you cannot use this well-known symbol of a battery, because you may think that a battery is also a source of power, but in this case it is specific. A power supply has this circuit symbol, so it is this circuit symbol that you use and not this, because if you use this circuit symbol, it means that you're saying you are referring to a battery, but in this case it is a power supply that the examiner said. Okay, so the components would be connected as shown. So we have that. Okay, and we also have our resistor connected to a power supply. Alright, so this is positive and this is negative. So this is the thermistor, this is the resistor, and this is the power supply. Question Z2. Explain how a transistor acts as a switch. Alright, this is very interesting. Okay, so how does a transistor act as a switch? Remember, the circuit symbol of a transistor, specifically an NPN transistor. So this is the circuit symbol of an NPN transistor. It is something like this, and it has 3 parts. This part is called the base, and for an NPN transistor, I'm being specific, this part is called the collector, and this part is called the emitter, because we have another type of a transistor which we call a PNP. They are different. An NPN transistor is different from a PNP transistor in that, in this case, okay, we'll get to see the difference as we progress in answering the question. Okay, so we have the base like that. All right, how does a transistor act as a switch? A transistor acts as a switch because it switches off a large current through the collector to the emitter. Right, so this is where the difference lies between an NPN transistor and a PNP transistor, because for an NPN transistor, current flows from the collector to the emitter, whereas for a PNP transistor, current would flow from the emitter to the collector. So in this case, we are only considering an NPN transistor. Okay, so what will happen here is something that is very easy to understand. Okay, so we've established to say that the transistor acts as a switch by switching on and off, switching on or off a large current flowing through the collector to the emitter. How does it do it? So it does this using this mechanism. So we have this part here called the base. This part here called the base works in such a way that if a current flows through this base, which we call a base current, then the transistor will conduct electricity between the collector and emitter. Okay, then if we don't have a base current through this base here, the transistor does not conduct electricity between the collector and the emitter. So it is off in a situation where there is no base current, and it is on in a situation where there is a base current. That is the basic idea. So here I wrote my answer to be that a transistor switches a large current through the collector to the emitter circuit when a small current passes through the base. Okay. Furthermore, when the base current is on, the transistor acts as a closed circuit, meaning that when the base current is on, the transistor will allow the conduction of current from the collector to the emitter, whereas when base current is off, the transistor acts as an open switch, meaning that the transistor does not allow the conduction of electricity or simply conduction of current from the collector to the emitter. Alright, that is it for the section A part of 2025 GCE. If you found this content useful, please consider subscribing to broaden this channel. Otherwise, thanks for tuning in.